Okay, so this is for Chapter 11, Video Assignment 1. With all the information that's given, the first thing it asks us to calculate is the molarity of N2 in blood that is in contact with air at atmospheric pressure. So, we're going to do that. Here I have part A, in contact with 1.0 atmospheres. That's normal atmosphere pressure. So, we're going to calculate that by using Henry's law, which says that molarity equals a certain atmosphere times the constant for Henry's law. In this case, Henry's law constant for dinitrogen in water is 3.8 times 10 to the negative fourth meters per atm. So we're going to calculate M by multiplying across, which is the same. So molarity of nitrogen in blood that is in contact with air at atmospheric pressure is 3.8 times 10 to the negative 4 meters. That's our first answer. Now, the second part is to determine or calculate the molarity of N2 in blood that is in contact with air at 4.0 atm, the pressure at a sea depth of 100 feet. So in that case, we're going to use the same equation setup, but instead of 1 atm, we're going to use 4 atm. So multiplying across, canceling out these two units will give us 0.00152 m, which is the molarity of N2 in blood that is in contact with air at 4.0 atm. So there's part B, I guess you could say. The next thing it asks for is to determine the volume of N2 that will be released from 5 liters of blood, roughly the amount of blood an average adult has if the deep sea diver rapidly ascends to the surface and the air goes from 4.0 atm to 1 atm. So, for this next part, part C, the first step is going to be to find the difference in molarity that is found in N2 between 4 atmospheres and 1 atmosphere. So taking that difference, 0.00152 minus 3.8 times 10 to the negative fourth, that's going to give us 0.00114 moles of N2 per 1 liter. That's the difference in molarity, because the diver is going from 4 to 1 atm. So that's why we find that difference. And then transferring that to 5 liters of blood. Using this conversion, 5 times 0.00114 equals 0.0057 moles of N2 per 5 liters. So this right there is the value that we will be using with the ideal gas law, Pervner, to be able to find V. We already have the pressure, which is 1 atm, which is what he's going to. N equals 0.0057 moles of N2. R is always going to be 0.08211 liter atmosphere per mole K. And then temperature in Kelvin. And so we find that temperature in Kelvin by taking the 37-degree body temperature and transferring that to Kelvin, which is 310 Kelvin. So everything I just explained is right here. 1 atm, that's the P, pressure. V, that's what we're trying to solve for. And then you have N, 0.0057 moles of N2, 310 Kelvin, and that's the constant. And let's see. So then we're just going to multiply all across right there to get a value of 0.145 liters of N2 that is released from 5 liters of blood as the deep sea diver rapidly ascends to the surface, going from 4.0 0.0 atm to 1 atm. That's that answer. 0.145 liters. Okay, now in the final part, we're going to be looking at if this escape happens in the form of bubbles at 1 millimeter diameter. Sorry, I didn't mean to erase all this word. So, we're looking at part D right here. Just ignore all this. But part D asks for 1 millimeter diameter bubbles. So for the first thing we have to do is to find how much of a volume that is. How much volume is enclosed in a sphere or a bubble with 1 millimeter diameter. Using the 4/3 pi r cubed volume of a sphere, we can take the diameter divided by 2 to have a radius of 1/2, and then multiply across 4/3 pi half cubed. It's going to be 0.52 millimeters cubed, which would equal the volume, or another way to put 0.52 millimeters cubed is 0.00052 milliliters, because 1 centimeter cubed is equal to 1 milliliter. So with that value, I would just, 1, 2, 3, 4. Moving the decimal place is 4 to find the milliliters cubed, or the milliliters. And so from there, we're going to divide the amount of liters that we found from the previous part, which was 0.145 liters. We're going to transfer that to milliliters, which is 145 milliliters, and then divide that by this value that we found right here, 0.00052 milliliters, that is found in one bubble. 0.00052 milliliters, and that is going to equal the amount of bubbles that escapes during this per liter of blood. Well, that's going to be, sorry, that division problem that we just did equals this value, 278,846 bubbles per 5 liters, which is what we found in the previous problem. This last part is asking per liter, and so we're going to transfer that to 1 liter. So 278,846 divided by 5 is going to equal this value of 55,769 bubbles per liter of blood. So that is the final answer on that part. And there you have it.